So now let's look at doing some application problems for differential equations for a higher order. So we're going to look at some linear models, initial value problem ones. We're going to be looking at some second order differential equations with constant coefficients. This would be looking like an equation that would be a times the derivative of y with respect to t, the second derivative, plus b times the first derivative of y, plus c times y equals g of t. And its initial value problem, so you'd have y of 0 equals y0, y prime of 0 equals y1. And g of t is your input force or your driving force or your forcing function. And what you want to do is you want to be able to find y of t, which is your output or response. One application is a spring mass system. In a spring mass system, we can have lots of different things that can happen. One of the things that we can look at is a free undamped system. So what we mean by undamped is that we actually have a spring that is in space. I'm going to go ahead and draw some pictures of this, of what I mean by this. And you might have some, let's say some surface you're attached to, and you attach a spring to that surface, and then you put a mass on the bottom of that spring. And that mass will stretch the spring down. If we do it in an ideal situation, which of course isn't ever going to happen, but let's just say we're in an ideal situation, then we wouldn't have anything else acting on it besides a couple of things. So first off, we are going to stretch it. We're going to put a mass on that. It will stretch it from where it was originally. So we might have a spring that's of this length, and then the mass will stretch it. So this distance that gets stretched is we're going to call it, let's call it S for something to call it. And so that's how far the spring is stretched. And when it gets stretched, it's going to be in a new position. I'm going to call this position equilibrium. And then what we're going to do is we're going to measure from that equilibrium position a certain distance. And so everything we're going to measure from that equilibrium position, we're going to call downward. We're going to just kind of get, you kind of need axes here. Think of this as your origin. You've got up and down. We normally call this the y-axis, so we're going to go with the y-axis. I think the book might call it the x-axis, but I like the y-axis better. And then a couple other things about this is normally positive is up, but what we're going to do is we're going to make positive down. So now what we're going to do is we're going to look at the fact of what things are acting on that spring. So let's just do a free force diagram. A force diagram, we have some things acting on that spring. We have the force due to gravity, which is going to be pulling down. And then we also have the spring force, which is the spring is trying to get back to its natural length. So it might be down here, but it's trying to get back to this natural length that it was originally. And so we're going to call that the spring force. And those are the only two forces that are acting on this if it's not moving. So if it's not moving, we're in equilibrium, nothing else is acting on it. Newton's second law tells us that the sum of the forces would be the force due to gravity, which is down, which we're calling positive down, minus the force of the spring, which would be up, because it's the opposite direction. Because we're not moving, nothing's moving, it's just sitting here. And that's going to equal 0 because nothing's moving. So the force due to gravity is equal to the spring force. And again, they cancel each other out, so you can kind of think of it as what that would be equal to. Now, one of the things we notice is that the spring force it's trying to restore the spring back to its normal length. It's trying to get it back to its normal length. So it's down here. The spring force will be trying to get us back that distance x, try to get back up to, or the distance y. So we want to try to get back to that. And if we're up here, it's going to try to push it back down. It's always opposite the direction of the travel, what we're traveling. And we're going to think of it, it's always opposite, the sign of it is always opposite the distance it's traveling. So if we're looking at the spring force is actually equal to minus some constant times x. Because all it's trying to do is get it back to its distance, back to its equilibrium, back to its normal length. It's really what it's trying to do. So we've got this force and we've got this some constant, and we call that constant the spring constant. This actually depends on the spring itself, the type of material it is, how tightly wound it is. There's lots of different things that it depends on of what it is. And you can calculate that by actually putting a weight on it, measuring how far it goes, putting another weight on it, measuring how far that one goes, how far it is from its length. And you could keep doing that and then plot it up, and you would actually be able to find out what K is, because you'd be able to figure out what the force of the spring is and what X is, and then K would be what you'd be left with. It'd be that slope. So it'd be easy enough to find out what K is. Now let's say we put this thing in motion. So now it is in motion. The force due to gravity and the force of the spring are already canceling each other out. So we don't need to worry about the force due to gravity. But we need to think about, again, what forces are acting on this. So if it's in motion, the sum of the forces by Newton's second law is mass times acceleration. And the only force that will make it actually move at this point is that spring force. So we would have this minus K times, I wrote X, I meant to write Y, because we're using Y as our variable here. So minus K times Y. And so what we have to do is just kind of figure out what this equation would look like. And remember A, and again, the minus is because if you're above equilibrium, you're going to try to go back to equilibrium. If you're below equilibrium, you try to go the opposite direction. So you always opposite your Y, your distance you're traveling. Acceleration is the second derivative of your position. So Y double prime is equal to minus K times Y. So here's my differential equation. M times Y double prime plus K times Y equals 0. And that is our differential equation. And then we can go ahead and solve that differential equation quite easily. You can either do it by just taking the integral of both sides, or you can do it by the idea of setting up your auxiliary equation. What I will do first is I'm going to get rid of this M. I don't like it there. So Y double prime plus K over M times Y equals 0. And so now that I've done that, what I can see is that I can actually call K over M. I can give it a new name. It's just a constant. Let's just give it a new name. I'm going to call it omega squared. And you're going to see why the square, it just makes life a little bit easier on us when we do calculations. So now we have Y double prime plus omega squared times Y equals 0. And we're going to go ahead and solve that. So that would be, if we go to the auxiliary equation, M squared plus omega squared equals 0. So M squared equals plus or minus omega I. And this is why we squared it, so that when we took the square root, we just get omega without anything. And we know that this would be Y of t would be C1 cosine of omega t plus C2 sine of omega t. So this is actually what we call simple harmonic motion. And I want to look at what this looks like. So I'm going to stop sharing for just a second. And I'm going to share something different. So give me a second here. And I'm going to show you a program I have on my iPad. And here's my iPad. So what I have is, this is what simple harmonic motion would look like. I'm going to go ahead and play this and show you what happens. This spring is, can't do that, sorry. I'm going to go ahead and play it. So it's moving up. Now we're going to go put it in motion. Notice it's just going to keep going. You can see it is that sine and cosine. Makes sense to be a sine and cosine functions. The red is the velocity. The blue is the position. And so you can see that the velocity and position are opposite each other. As you get to a minimum of your position, you're going to have a zero velocity. You get to a maximum of your position, you're going to have a zero velocity. The velocity is maximum and minimum at the inflection point. So all the things we know from calculus is happening here. And this is what's known as simple harmonic motion. This will never, ever, ever, ever end. All right, now that's not really the the real thing that's going to happen. So let's look at what really can happen. So back to sharing my screen again. So you can actually look at different things. You can talk about the frequency. You can talk about different things with this, but we're just going to look at this at the moment. And so now we're going to talk about what would look like if we had what we call free undamped motion. In other words, we're not going to put this in some space. It actually will slow down. There will be some dampening happening to this. And so I'm actually going to go ahead and I keep doing this, and I'm sorry, but I'm going to share my screen again with my iPad. And so what we do is we're going to look at what that's going to look like. So what I'm going to do is I'm going to actually add in a dampening factor. And the way I can do that is if I look up here, this is my differential equation, but notice there's a by prime term. But when I did my free undamped motion, my free motion, I didn't have this y prime term. So I wonder what will happen if I change that. So let's actually change that y term. Let's go ahead and make that into, I don't know, maybe 1 instead. And so now I'm going to go ahead and play this and show you what happens when I have a dampening. So as you look at this, you can see this position going. The velocity is obviously getting slower. The velocity is actually getting smaller and smaller and smaller, and the amplitude of my distance away is getting smaller. So the dampening is kind of like resistance, air resistance, friction. Those are all things acting. If I increase my dampening to, let's say, maybe 5 this time, then you notice that when that happens, I get even less oscillation happening. So think of this as you have something in water. You're not going to have much, you have a lot of dampening in water. It's not going to do very well. And it's going to move like this, and it's not going to oscillate a lot. So what I want to do is I want to look at how can we actually see what's happening with this. So let's go look at how we can actually talk about what this will do. So again, this dampening force, it's actually proportional to the derivative. And I know I've got an x there, we'll make it into a y. So it actually is derivative that we're working with. And it's velocity. So the dampening force is actually proportional to the velocity. And we're going to call it beta times the velocities because we need some proportionality constant. I can't call it K because we use K for something else. I can't call it C because we use C for lots of other things. So we now have that. And when I have that to look at, I can now see what could actually happen with this. So now my dampening equation, my equation now becomes that we have our original equation, which was the second derivative of velocity, of position, times the mass, plus, and I'm going to go ahead and go over here, we had the k times y equaled 0. But now what we're going to do is we're going to have this dampening factor in here. And so we're going to have beta times dy dt. So now we have a new differential equation that we're working with. And we still will be dealing with information from here and still be going things. It's still going to be initial values. So you're still going to have y of 0 is y0, and y prime of 0 is v0, some initial velocity. So we can have this information and we can look what happens. Again, let's go ahead and get rid of the m. So we're going to divide through by m. And remember, we already called k over m omega squared. Let's call the beta over m something, and let's actually call that 2 lambda. And you'll see why the 2. Again, a lot of times what we do is we pick one variable from something, and then we realize, oh, it'd be a lot easier if it was this. And it just makes our mathematics a little bit easier to deal with. So we now get the second derivative of y plus 2 lambda times the first derivative of y plus omega squared times y equals 0. And now let's see what could happen with this. We can actually think about solving this. So the auxiliary equation would be m squared plus 2 lambda times m plus omega squared equals 0. It's a quadratic equation. You can solve this with the quadratic formula. You solve it with the quadratic formula, you get that m1 is minus lambda plus the square root of lambda squared plus omega squared. So this is why we picked the 2 lambda, because if you pick 2 lambda, you'd have a 4 lambda squared plus 4 omega squared. And here, if you're using the quadratic formula, the 4 come out as a 2. And remember, this would be all over 2a, and the 2's would all cancel. So by calling it 2 lambda, this is what happens. M sub 2 would be minus lambda minus the square root of lambda squared plus omega squared. So remember that would mean that my solution, y of t, would be c1 e to the minus, well, let's just call it m1, instead of trying to make it really complicated looking, m1 times t plus c2 e to the m2 times t. And remember, these can change depending on what m1 and m2 actually are. So let's look at some different situations. Let's look at the case 1. And case 1 would be that we have 2 real solutions, 2 real roots. Well, to have 2 real roots, that means that the thing under the square root has to be positive. So that means that lambda squared has to be greater than omega squared. All right, so that would get me y of t would be c1 e to the m1t plus c2 e to the m2t, because they're 2 real roots, it all works out beautifully. Great. Now let's look at case 2. Case 2 would be 1 real root. And that would mean that lambda squared actually equals to omega squared. Remember, in that case, we want different roots. So we know that one of them is c1 e to the m1t. The other one would be c2 t e to the m1t. And then the next thing is case 3. And that would be 2 complex roots. And that would happen if omega squared is bigger than lambda squared, because then you'd have a complex number. And then your y of t would be, well, you'd have e to the minus lambda t, because that's your real part, times c1 cosine of your imaginary part. And your imaginary part is the square root of omega squared minus lambda squared, because we want it to be positive. And omega squared is bigger, so we put that one bigger first. It gets rid of the I, plus c2 sine of the square root of omega squared minus lambda squared. And so there's those solutions we could have. And what I want to do is I want to think about what would give me what those graphs would look like. So let's go back to our iPad, looking at see what that looks like. So give me a second here. Oops, it was already mirroring. Okay, so now we have this. And what I want to do is I want to look at what it would look like. So notice in this graph, my B was fairly large and we didn't have any oscillations going on here. If I made my B small again, then we have oscillations. So notice we do in fact have oscillations here. If I make my B somewhere in between, so let's say it's 2, I have oscillations, but not as many oscillations. If I make my B 3, notice I pretty much have very little oscillation. Let's go with 4. And notice I pretty much have no oscillations, and it just kind of is going to get slowly into, if you look at this graph of what it's doing, you're going to get slowly into a nice, remember the red is the velocity. So your velocity is going to decrease really fast and it's going to slowly come to 0. The position is going to kind of go down and slowly go to a position of 0. So you're trying to get the equilibrium. Let's go really crazy with this. Let's make this like 20. And when it's 20, notice what's going to happen is you're going to have a really quick, fast drop, and then you're going to slowly, really slowly come to the end. We're going to have this violent drop, and then a violent drop here. So it looks like what could happen there. And I'm going to go ahead and look at some other models. We actually have some models we can look at. I keep doing that. We're going to look at what we call overdamped. And an overdamped, notice it is in fact oscillating. So that is when our B is kind of small. Notice here the B is somewhat small. It's around 1, and we will get that oscillation. We'll look at a different model. This one's going to be overdamped. So that one was underdamped. This one would be the overdamped. Notice here, again, we've got a B of about 5. Notice it kind of is getting to equilibrium, but it takes a lot longer to get there. Let's do another one. Let's do a model that is what we call critically damped. And notice when we're critically damped, we actually do get down to equilibrium kind of fast. We're much faster getting equilibrium than the overdamped does. And so you can kind of think of your overdamped as it just takes too long to get where you are. And a way I like to think of this is with models, an underdamped one is if you're driving in your car and your shocks in your car are going bad, you hit a bump, you're going to be constantly bouncing over and over and over again because there's not enough dampening in those shocks to actually get you to slow down and stop bouncing. So that would be an example of an underdamped. Overdamped one, here you would actually feel kind of, you're not going to gently get to the equilibrium. You're going to kind of bounce into it and it's not going to feel good. And so that would be your overdamped. And your critically damped is going to just slowly get you back, not too slow. You don't take a long time to get there, but you're not going to just kind of have this much longer, like you're feeling like it's never going to get you down there. So your critically damped is the one we like the best. It's where you've got the best dampening happening. So what I want to do now is I want to kind of summarize all this as to which one of these situations will get you these different ones. So we'll stop sharing for a second. And so in all these cases, with the complex roots, you get the cosine and sine. So that must mean that this one is the underdamped situation because you're going to constantly be going up and down, up and down. So this is an underdamped. So and when you have real roots, you actually will kind of slowly get down there. You're going to be kind of this overdamped. So this one's an overdamped. And this one here, where you have a T factor involved here, you're actually going to get your critically damped. All right. So now what I'd like to do is I'd like to actually, let's do an example of this and talk about what this would look like. So a 4-foot spring measuring 8 feet long after a mass weighing 8 pounds is attached to it. The medium through which the mass moves offers a dampening force numerically equal to the square root of 2 times the instantaneous velocity. I like to find the equation of motion if the mass is initially released from the equilibrium position with a downward velocity of 5 feet per second. And I'd like to find the time at which the mass attains its extreme displacement from the equilibrium position. And we want to know what is the position at the mass at this instant. So I may not do all of this, but see how far we want to get. But let's at least get started into this. So we have to talk about a few things. We know the mass. Actually, we don't know the mass. We know the weight. So we know the weight of the object. We know the weight of the object was 8 pounds. Can we find the mass? Well, remember, mass times gravity is your weight. So mass times acceleration due to gravity, excuse me. So you've got to have mass times the 32 feet per second squared is going to equal 8. So your mass is 1/4 of what we call a slug. So there's your mass. We also need to know what is the K. We need to find out what our spring constant is. So one of the things I notice in here is that we have a 4-foot spring that measures 8 feet long after the mass weighing 8 pounds is attached to it. So we have this 4-foot spring. So think of it this way, you've got the spring that's 4 feet. You then stretch it to 8 feet. So we want to find this distance it travels here. We're going to call that again S. And so S would be 8 minus 4 in this case, or 4 feet. Okay, so now the next thing we need to find out is what is my K actually equal to? So remember your spring constant, mass times gravity, the acceleration due to gravity, is equal to K times S. If we're stopped, if we're not going anywhere, because remember they cancel each other out. The force due to gravity cancels out the spring force. So these all nicely cancel each other out if it's not moving. So my mass, which we know is 1/4, gravity we know is 32 feet per second, K is what we're trying to find, and we just found S was 4. So therefore we can find out that K is actually equal to 2. And by the way, the units on that, let me give myself some space to put the units here, is this would be in pounds, because 32 times 1/4 is your pounds, and the 4 was in feet. So the units on K is 2 pounds per feet, or pounds per feet is that. Okay. Now the next thing we need to figure out is we now know what K is, we know what M is, but remember we're working with this equation that also has to deal with the mass, the force, the mass and the acceleration, and then also the dampening force. So let's find out the dampening force. And it says the medium through which the mass moves offers a dampening force numerically equal to the square root of 2 times the instantaneous velocity. So your dampening force, we're going to call it F sub dampening, is numerically equal to the square root of 2 times the instantaneous velocity. So y prime is my instantaneous velocity. And so that tells me that beta is the square root of 2. So now we have that mass, which is 1/4 times y double prime. So this is Newton's second law, plus the dampening force, which is beta square root of 2 times y prime, that dampening force, plus the spring force, which we just found out was 2 times y equals 0, because we have no driving force. So there is my differential equation that I want to solve. Let's see if we can get to the initial value problem. So what is my position at time 0? So let's go back up to the problem and see where it was initially. And we're told initially is being released from equilibrium. And x is our distance from equilibrium. So initially we're at 0 feet. We also need to find out our initial velocity. So again, going back up here, we have to have an initial velocity, or we have to have an initial position, because otherwise it won't go anywhere. And here we are told that we're released with a downward velocity of 5 feet per second. So remember, downward here is positive. So it's going to be positive feet per second, 5 feet per second. All right, so there's all of our information. We can now solve this. You can either do this using Laplace transforms. You can do this using the auxiliary equation. I don't really care. I will go ahead first and get it with a y prime, y double prime with nothing in front of it. So we're going to multiply through by 4. So then we get 16, I'm sorry, 8y. Whoops, can't multiply. So 8y equals 0. So I'm going to go ahead and do this one using the auxiliary equation. So m squared plus 4 square root of 2m plus 8 equals 0. I'm then going to go solve this. I find out that when I go to solve this, that m is equal to plus or minus 2, I'm sorry, just minus. Sorry, m is just equal to minus the square root of 2. So that's what m is equal to. If I were to solve this equation, that's what I would find out my m is. That tells me my y of t is c1 e to the minus 2 square root of 2t. And my c plus c2 plus c2 times t e to the minus 2 square root of 2t. I need to find out what my c1 and c2 are. So y of 0 will give me c1, and that is equal to 0. So we know c1 is 0. Y prime of t, we already know c1 0, so you can ignore that. It's going to be c2 e to the square root of 2 square root of 2t plus, or actually let's just go minus 2 square root of 2 c2 t e to the minus 2 square root of 2t. Y prime of 0 would be c2 minus 2, well, the rest of that is 0 because you got a t in that. And that was equal to 5. So we now know c2 is 5. So we now know that y of t is equal to 5t e to the minus 2 square root of 2t. And there's your equation. This is critically damped because we have that form of critically damped. You can actually plot it up and you can see that. And then you can actually find the other pieces. Don't forget, if you want to find out where it's maximum, you find the derivative set equal to 0 to find your critical points and so forth. We also can have what we call free damped motion. Oops, I went to the wrong place. Sorry, we already just did that one. We can also have driven motion. And driven motion is where you would have the one side of the equation, m times y double prime plus beta times y prime plus k times y is equal to some force we're going to call g of t. G of t is the force that's moving it. It's making it go. It's going to constantly have it work. And so it allows it to actually be where the amplitude will be changing as that force is acting on it. And you can kind of watch what that would look like. And then see. And so if you want to solve this, you would solve either through Laplace transforms, or you could solve it using other factors and other things you can go into it. So graphically, what this would look like, and I'm going to go ahead and show you on my iPad again. So we'll go back into the iPad. And so we'll come back into here. And we can look to see what this looks like, if it ever gets there. Doesn't seem like it wants to connect. So if, oh, there it goes. Okay. So what I have here is I actually would have what we have a function. In this case, the function is cosine of 2t. And what you get is when you play this, you're going to see that we're driving this force. And when we're driving it, notice that the amplitude is changing on my velocity and on my position. It's changing a bit. So that's what's happening with this. You can see it's going faster, and you can see what's happening to this system. If we look at another case, so we'll do another model. We're going to do beats. And so here we're going to go ahead and play this one. And you can see what's going to happen with this is we're driving it by this 10 cosine of t over 5 function. And what happens is you're getting this kind of beat kind of idea happening. So those are what those would look like if we have that situation. And so that's what your driven motion would look like. The last thing I want to mention is the LRC circuit. If we happen to have a circuit, we can draw what that circuit looks like. We have a voltage source. So here's my voltage source. It would come along. We might go through an inductor. An inductor stores current. And then we might go through a resistor. And a resistor takes away some of the voltage drop through it. And then you might go through a capacitor. A capacitor stores charge. And Kirchhoff's laws says what we can do with this. We can start with E. We gain that as we go through E, so it's a positive. As we go through L, we lose some voltage. So we're going to lose some voltage going through L. L does save charge, so to save current source, the current is actually changing. So it's going to be a rate of change of current over time. Then when you go through the resistor, you also have a voltage drop. So it's minus R times I. That would be your voltage drop through resistor. As you go through the capacitor, you would also have a voltage drop, and that voltage drop is 1 over C times Q. We get back to where we started, so it now equals 0. So this is what it looks like in here. The different pieces that go on, but we have now too many letters going on. We have an I and we have a Q. So we don't want to have that many letters. We want to see if there's a relationship. And it turns out that I is equal to the rate of change of charge. That's actually what current is defined to be, is it's the change in the charge. The electrons are flowing, and that's what causes your current. So looking at this, if I'm taking the derivative of current, that would be the second derivative of charge. So E, I'm going to go ahead and get E by itself. So I'm going to take everything to the side. E would equal L times the second derivative of charge minus R times the first derivative of charge minus 1 over C times charge equals 0. Sorry, it doesn't equal 0 anymore because we let it equal E. And so since I let it equal E, I should have made these positives. Sorry about that. We make those positives. And this looks a lot like our equation that we had for springs, similar ideas. You would have an initial charge. So the amount of charge you'd have on initially, Q0, would equal some Q0. And you also could have an initial current. Remember, current is a derivative of charge, and that would be an initial current, I0. And you can then solve this same as you would do before. So if you, I should just call that I0, sorry about that. If you were to, E is what is considered your electron. If you have no E, then your electronic vibrations are free. If you have an E, then you have some forced vibrations going on. And you can also have critically damped, overdamped, and underdamped with this too. So that's some applications. that produce a second order differential equation.